Isaac Newton, Beyond Physics and Mathematics. When we utter the name Isaac Newton, most minds conjure images of falling apples, mathematical equations scratched onto parchment, and the cold mechanical universe of clockwork precision. This is Newton, the secular saint of science, the rational hero of the Enlightenment, the man who banished mystery from the heavens and replaced divine caprice with mathematical law. But this Newton, the Newton of popular imagination and textbook simplification, is a carefully constructed fiction, a sanitized myth that emerged only after his death when his intellectual heirs systematically suppressed half of his life's work. The real Isaac Newton was something far stranger, far more complex, and ultimately far more interesting than the myth allows. He was a man who spent more hours decoding biblical prophecy than deriving the laws of motion, who conducted dangerous alchemical experiments in secret laboratories, who believed that ancient civilizations possessed scientific knowledge later lost and corrupted, and who rejected the central doctrine of Christianity while maintaining absolute conviction in an active, present God whose very being constituted the fabric of space itself. To understand Newton's true legacy, the legacy that actually shaped the modern world, we must abandon the comfortable fiction and confront the uncomfortable reality. Newton was simultaneously the father of modern physics and a passionate theological heretic, a mathematical genius and an alchemical experimenter, an empiricist who established the experimental method, and a mystic who sought ancient wisdom in cryptic texts. These weren't contradictions in Newton's mind. They were aspects of a unified intellectual vision, a comprehensive system for understanding God's nature through every available source. The book of nature, read through mathematics, the book of scripture, decoded through prophecy, the book of matter, investigated through alchemy, and the book of history, reconstructed through chronology. Newton's birth in 1642, the year Galileo died, seemed almost providentially timed. He arrived at a moment of profound intellectual crisis. The old Aristotelian philosophy that had dominated European thought for centuries was collapsing under the weight of its own contradictions and the discoveries of the new astronomy. Copernicus had displaced Earth from the center of the cosmos. Kepler had discovered that planets moved in ellipses, not the perfect circles that ancient philosophy demanded. Galileo had revealed mountains on the moon and moons around Jupiter, shattering the distinction between corrupt terrestrial matter and perfect celestial substance. Descartes had proposed a radical new mechanical philosophy, reducing all nature to matter in motion governed by contact forces alone. Into this intellectual chaos stepped Newton, a solitary, obsessive genius from the English countryside, bearing a new vision that would prove more powerful than anything that came before. But Newton's achievement wasn't simply to perfect mechanical philosophy or to make Descartes' system work properly. It was to transcend mechanism altogether while appearing to perfect it, to smuggle God back into nature through the back door of mathematical law while claiming to have expelled final causes from natural philosophy. Newton's famous statement, "I frame no hypotheses, hypotheses non fingo," has been interpreted as the manifesto of pure empiricism, the declaration that science must restrict itself to what can be observed and measured. But this interpretation fundamentally misunderstands Newton's project. What he actually meant was that he distinguished rigorously between what could be demonstrated mathematically from empirical observation, true knowledge, and speculative mechanisms that might explain those mathematical relationships. He could demonstrate mathematically that bodies attract each other with force proportional to their masses and inversely proportional to the square of distance between them. He could not, and this troubled him deeply, explain how or why this attraction occurred. This distinction between mathematical description and mechanical explanation created a profound philosophical problem that would occupy thinkers for the next 2 centuries. Newton had created a physics more powerful than any before it, a mathematical system that could predict planetary positions centuries in advance with stunning accuracy. Yet, this very success came at the cost of abandoning the mechanistic ideal of explaining everything through contact forces and geometric extension. Gravity acted across empty space with no intermediary mechanism. How could this possibly work? What transmitted the gravitational force from Sun to Earth across millions of miles of void? Newton's private answer, one he dared not state publicly except in the most guarded terms, was that God transmitted it. Gravity might be nothing less than the direct action of the divine will, continuously present throughout all space, holding the universe together moment by moment through active power. This was why absolute space was necessary in his system. It wasn't merely a geometric abstraction, but the very sensorium of God, the omnipresent field of divine consciousness within which all material bodies existed and moved. This theological foundation made Newton's physics simultaneously more radical and more conservative than it appeared. More radical because it suggested that natural laws weren't autonomous mechanisms, but expressions of divine will, that nature operated through active powers and principles rather than passive matter alone. More conservative because it preserved a role for God, not as distant clockmaker, but as continually active sustainer, not as hypothesis to be dispensed with once mechanism was perfected, but as the fundamental ground of physical reality itself. Yet Newton understood that to state this theological foundation explicitly would be to invite the very charge he most feared, that his physics rested on metaphysical speculation rather than empirical demonstration. So he constructed an elaborate rhetorical strategy, claiming to derive his laws purely from phenomena through mathematical analysis, presenting himself as the modest empiricist who restricted knowledge to what could be proved. This strategy succeeded brilliantly, too brilliantly. His successors took him at his word, accepted the mathematical physics while discarding the theological framework, and created the secular mechanistic Newtonianism that Newton himself would have rejected as incomplete if not heretical. The man who emerges from careful historical study is far removed from the Enlightenment icon. Newton was notoriously difficult, prone to bitter priority disputes, capable of using his position as president of the Royal Society to crush perceived opponents. He was secretive about his theological views, knowing that his anti-Trinitarian heresy could destroy his career. He was obsessive about his alchemical experiments, sometimes working for weeks at the furnace with little sleep, seeking not just chemical transformations, but the active principles that governed matter at its most fundamental level. Newton never married, formed few close relationships, and devoted his formidable intellect to solitary study with an intensity that bordered on pathological. When he suffered a mental breakdown in 1693, possibly from mercury poisoning due to his alchemical work, his contemporaries worried he had lost his mind permanently. He recovered, but the episode revealed the physical and psychological cost of his obsessive pursuit of knowledge. His public life after the Principius publication in 1687 took an unexpected turn. Rather than continuing his scientific work, Newton became increasingly occupied with his appointment as warden and then master of the Royal Mint, where he pursued counterfeiters with the same obsessive energy he'd once devoted to mathematics. He spent his final decades not solving new problems in physics, but preparing new editions of his earlier work, writing theological treatises he never published, and conducting the chronological studies that attempted to establish accurate dating for ancient history through astronomical calculations. This later Newton, the administrative Newton, the theological Newton, the historical Newton, has seemed to many historians an inexplicable falling off from earlier genius. But this judgment reflects our categories, not his. For Newton, there was no fundamental distinction between natural philosophy, theology, chronology, and prophecy. All investigated the same ultimate reality, God's nature and God's plan for history, through different sources and methods. The mathematical physics revealed divine rationality expressed in natural law. The biblical studies revealed divine purposes expressed in historical providence. The alchemical experiments revealed divine activity expressed in matter's hidden powers. Understanding Newton requires grasping this unified vision and recognizing that the tensions and contradictions we perceive in his work, between empiricism and metaphysics, between mechanism and divine action, between public caution and private heresy, were the productive tensions that generated his extraordinary achievements. He created modern physics not by being a perfect empiricist or a perfect rationalist, not by being purely secular or purely religious, but by holding these tensions in creative balance. By building a system comprehensive enough to encompass both mathematical precision and theological conviction. This first chapter establishes what the following chapters will explore in detail: that Newton's legacy is far more complex, far more interesting, and far more relevant to understanding how science actually develops than the simplified myth allows. He was not the first modern scientist who transcended medieval superstition. He was the last great natural philosopher who attempted to hold together natural philosophy, theology, and ancient wisdom in a single comprehensive system. And the unresolved tensions in that attempt continue to shape how we think about science, knowledge, and reality itself. The collapse of Aristotelian philosophy and Newton's rise. To understand Newton's achievement, we must first understand what came before him and why it had failed. For nearly 2,000 years, European intellectual life had been dominated by Aristotelian philosophy, a comprehensive system that explained everything from the fall of stones to the motions of planets, from biological growth to political organization, from ethics to metaphysics. Aristotle's philosophy wasn't merely a collection of theories about nature. It was a complete worldview, a way of understanding how reality was structured and how knowledge of that structure could be achieved. At the heart of Aristotelian physics lay several principles that seemed self-evidently true to anyone who observed the world carefully. Natural motions were divided into two fundamental types: violent motions caused by external forces, like throwing a stone, and natural motions caused by objects seeking their natural place, like stones falling toward Earth's center or fire rising toward the heavens. Every substance had a natural place in the cosmic hierarchy, and when displaced from that place, it naturally moved back toward it. Heavy elements, earth and water, naturally moved downward toward the cosmic center. Light elements, air and fire, naturally moved upward away from the center. This explained why stones fell. They were composed primarily of earth element, and thus naturally moved toward Earth's center where all earth element belonged. It explained why fire rose. It was naturally light and sought the upper regions. It explained why the celestial bodies moved in perfect circles forever. They were composed of a fifth element, quintessence or ether, whose natural motion was eternal circular revolution. This system had enormous explanatory power for everyday experience. It accorded perfectly with common sense observation. Heavy things do fall down. Fire does rise up. The celestial bodies do appear to move in regular circles. Moreover, the system was beautifully integrated with Aristotelian metaphysics, ethics, and even theology. The cosmos had a clear structure: imperfect, changing terrestrial region below the moon, perfect, unchanging celestial region above. This cosmic structure reflected and reinforced social hierarchies and moral values. Higher was better, more perfect, closer to God.
Lower was worse, more corrupt, farther from divine perfection. But by the early 17th century, this entire edifice was crumbling. The breakdown occurred on multiple fronts simultaneously, each discovery or argument undermining another pillar of the system until the whole structure collapsed. The astronomical revolution. Copernicus's heliocentric system, published in 1543, had placed the Sun, rather than Earth, at the center of planetary motions. Initially dismissed as merely a mathematical convenience, the Copernican system gained support from Kepler's discovery, 1609, that planets actually move in ellipses with the Sun at one focus, not the complicated combinations of circles that both Ptolemaic and Copernican astronomers had assumed.
If the heavens themselves didn't exhibit the perfect circular motions that Aristotelian philosophy demanded, what happened to the distinction between perfect celestial and imperfect terrestrial regions? Galileo's telescopic observations, 1609 to 1610, provided even more damaging evidence. The moon had mountains and craters. It was made of the same kind of imperfect, changeable matter as Earth. Jupiter had moons orbiting it. There was more than one center of motion in the cosmos. Sunspots appeared and changed. The sun itself was imperfect and mutable. Venus showed phases like the moon. It must orbit the sun, not Earth. Each observation chipped away at Aristotelian cosmology's foundations. The problem of projectile motion. Aristotelian physics had always struggled to explain projectile motion, why an arrow continues moving after leaving the bowstring, why a thrown stone doesn't fall straight down immediately. Aristotle had proposed that the air itself pushed the projectile along, but this had never been satisfactory. By the late medieval period, theorists like Jean Buridan had proposed impetus theory, that violent motion imparted a kind of internal force to the moving object that gradually dissipated. But this required abandoning the principle that all motion required a continuous external mover, one of Aristotelian physics's fundamental axioms. Galileo's careful studies of motion down inclined planes and of projectiles revealed mathematical regularities. Falling bodies accelerate uniformly. Projectiles follow parabolic paths that couldn't be explained by Aristotelian natural place theory. Objects didn't naturally seek their place through some internal tendency. They moved according to mathematical laws that had nothing to do with elements seeking their natural locations. The mechanical philosophy. Descartes proposed a radical alternative. Perhaps all natural phenomena could be explained by matter in motion according to geometric principles alone. Instead of mysterious natural tendencies and final causes, perhaps there was only extension, matter as spatial occupancy, and motion communicated by direct contact. Planets moved not because they naturally loved circular motion, but because they were caught in vast vortices of subtle matter swirling around the sun. Objects fell not because they sought Earth's center, but because subtle matter pressed them downward. This mechanical philosophy had enormous appeal. It promised to reduce all of nature to clear and distinct principles, extension and motion, that could be understood through mathematics and geometry. It eliminated occult qualities and final causes, making nature purely mechanical and potentially completely comprehensible. It fit the new mathematics, analytic geometry, which Descartes himself had invented, which reduced geometric relationships to algebraic equations. But Cartesian mechanism had its own severe problems. Descartes' explanation of planetary motion through vortices couldn't account for Kepler's laws. His laws of impact, how moving bodies transferred motion through collisions, were demonstrably wrong. His identification of matter with extension had bizarre implications.
It made vacuum impossible by definition, and suggested that the entire universe was one continuous substance with no real distinction between bodies. His reliance on God to preserve the total quantity of motion in the universe seemed like special pleading, an admission that mechanism couldn't be self-sufficient. The void and atomism. Ancient atomism, revived by Gassendi and others, proposed another alternative. Perhaps nature consisted of indivisible atoms moving through void space, colliding and combining according to purely mechanical principles, without Descartes' problematic identification of matter with extension. This restored the possibility of void space and allowed for discrete bodies rather than one continuous plenum. But atomism faced its own difficulties. How did atoms stay together to form stable bodies? What explained the rich diversity of natural phenomena using only atoms and void? Most troubling, atomism seemed to make nature purely mechanical and deterministic, leaving no room for divine providence or human free will, a theologically dangerous position in the 17th century. By the time Newton began his serious scientific work in the 1660s, natural philosophy was in crisis.
Every available option had severe problems. Aristotelianism contradicted too much empirical evidence and couldn't accommodate the new astronomy. Cartesian mechanism couldn't account for Kepler's laws and contained logical difficulties. Atomism worked in some domains but seemed incomplete and theologically problematic. Mathematical description, Kepler's laws, Galileo's law of falling bodies, provided accurate predictions but no causal explanations. Newton's genius lay in recognizing that a new synthesis was possible, one that would preserve what worked in each approach while transcending their limitations. From Aristotle, he would retain the concept of natural forces and powers operating in nature, but mathematical rather than qualitative. From Descartes, he would take the mechanical approach and the use of mathematics, but reject the identification of matter with extension. From atomism, he would accept discrete bodies and void space, but add forces beyond mechanical contact. From mathematical astronomy, he would take the empirical constraint that any theory must match observed phenomena, but insist that mathematical description must be grounded in causal principles. The result would be something unprecedented, a mathematical physics that described natural phenomena with quantitative precision while remaining agnostic or deliberately obscuring the ultimate mechanical causes. Newton would show that bodies attract according to an inverse square law without explaining how or why. He would demonstrate that this single principle, combined with his laws of motion, could explain everything from falling apples to planetary orbits, from tides to the precession of the equinoxes. The empirical success would be so overwhelming that the lack of mechanical explanation would be forgiven, or at least postponed. But this synthesis required something more, something that distinguished Newton from both his predecessors and most of his successors, a metaphysical foundation that could support action at a distance without reducing to either Aristotelian occult qualities or Cartesian mechanical impossibility. That foundation would be absolute space, identified with divine omnipresence, the subject of our next chapter. The collapse of Aristotelian philosophy created the space for Newton's achievement. The old system's failure meant that any new system that could provide empirical success while maintaining some philosophical coherence would be welcomed, even if it left fundamental questions unanswered. Newton exploited this moment brilliantly. He created a physics powerful enough to establish itself through practical success, philosophically sophisticated enough to seem more than mere mathematical description, yet strategically obscure about ultimate causes that followers could interpret it in multiple ways, as mechanism perfected, as divine action mathematicized or as pragmatic instrumentalism postponing metaphysical questions. This strategic ambiguity was not confusion, but genius. It allowed Newtonian physics to triumph while the philosophical battle over its meaning continued for centuries, driving development in both physics and philosophy. The collapse of one comprehensive system, Aristotelian philosophy, led not to another comprehensive system, but to a productive tension between mathematical success and philosophical uncertainty, a tension that characterizes modern physics to this day. 3. Absolute space, God's omnipresence in Newtonian thought. At the heart of Newton's natural philosophy lies a concept so strange, so metaphysically loaded, and so philosophically problematic that philosophers have been arguing about it for over 3 centuries: absolute space. This wasn't merely a technical device for solving physics problems. It was Newton's most radical metaphysical commitment, the foundation on which his entire physical system rested, and, most controversially, his way of placing God directly at the center of natural philosophy without appearing to invoke divine hypotheses. To understand why absolute space was revolutionary and why it mattered so profoundly, we must first grasp what Newton was rejecting. Aristotle had conceived space as relational. An object's place was its relationship to surrounding bodies, particularly the innermost boundary of what contained it. There was no empty space in Aristotelian physics. Nature abhorred a vacuum. Epistemological. How can we know absolute space exists if we can only ever observe relative positions and motions? Because we know God exists and is omnipresent, and space is the structure of that omnipresence. Theological. How is God related to the natural world? Not as distant creator who set mechanism in motion and withdrew, but as continuously present ground of spatial reality itself. God is not in space the way bodies are in space, rather space exists because God is omnipresent. This theological foundation for absolute space explains several otherwise puzzling aspects of Newton's system. Why gravity might be direct divine action. If space is constituted by God's presence, and gravity acts across space without material medium, perhaps gravity is nothing other than God's will continuously directing bodies toward each other according to mathematical law. Newton couldn't say this explicitly without seeming to make physics dependent on theological hypotheses, but his private writings suggest he believed something like this. Why Newton cared so deeply about space? The debate over absolute versus relational space wasn't mere technical physics, it was about God's relationship to nature. Leibniz's relational space, which we'll examine in detail later, implied that God wasn't necessarily present in nature continuously. Newton's absolute space made divine presence the foundation of physical reality. Why space is Euclidean and infinite? Because God's omnipresence is perfect, unlimited, and geometrically structured. The geometric properties of space reflect attributes of divine consciousness. But this theological grounding also created severe philosophical problems that would occupy thinkers for centuries. The unobservable absolute. If absolute space is real and provides the true reference frame for motion, but we can only ever observe relative positions and motions, how can we access this absolute frame? Newton needed absolute space for his physics to ground absolute acceleration, but his methodology demanded that physics be based on observable quantities. This tension was recognized immediately and exploited by critics. Space as entity. Making space real and independently existing seemed to multiply entities unnecessarily. Leibniz attacked this as violating parsimony.
Why posit this strange, immaterial, infinite, eternal entity when relational space, space as just relationships between bodies, would suffice? The necessity puzzle. If space is identified with God's omnipresence, is space necessary? Couldn't fail to exist? This seemed theologically problematic. God's existence might be necessary, but should the particular geometric structure of space be necessary too? What if God had chosen to create space with different geometry? Action at a distance. Even with absolute space providing the geometric arena, the problem of how gravity acts across space remained. If space isn't a material medium, what transmits gravitational force? Newton's hint that it might be direct divine action satisfied few philosophers and seemed to many like giving up on proper natural philosophy. Despite these problems, Newton's concept of absolute space became foundational to physics for 2 centuries. Partly this was because his physics worked so well that philosophers were willing to accept metaphysical difficulties. Partly it was because most physicists simply ignored the metaphysical questions and treated absolute space as a useful mathematical framework without worrying about its ontological status. But the unresolved tensions remained productive. The debate between absolute and relational space drove Leibniz to develop his philosophy of monads and pre-established harmony. It led Berkeley to his idealism, arguing that space exists only as idea in minds human and divine. It pushed Kant toward his revolutionary claim that space is neither absolutely real nor purely relational, but rather the a priori form of outer intuition, the structure that minds impose on experience to make experience possible. Even in modern physics, echoes of Newton's absolute space remain, though transformed. Einstein's theory of relativity rejected absolute space and absolute time, replacing them with relativistic spacetime. Yet even relativistic spacetime has geometric structure independent of matter. It's not purely relational. And the debate continues. Is spacetime substantival, existing independently, or relational, merely a mathematical description of relationships? Is geometry determined by matter's distribution, or does spacetime have its own dynamics? Newton's theological motivation, the identification of space with God's omnipresence, was quietly dropped by 18th century Newtonians who wanted to secularize his physics. But this created a problem. Without the theological foundation, what justified absolute space's existence? The physics seemed to require it, especially for understanding rotation and acceleration, but the metaphysics became obscure. This obscurity was actually advantageous. It allowed scientists to use absolute space pragmatically without defending it philosophically. When philosophical problems became too pressing, scientists could retreat to instrumentalism. We don't know what space really is, but treating it as absolute gives us a useful reference frame for calculations. This instrumentalist attitude, using concepts that work predictively without worrying too much about their metaphysical status, became characteristic of modern physics. Yet Newton himself would likely have rejected this instrumentalism. For him, absolute space wasn't merely a useful fiction, but a genuine insight into reality's fundamental structure. A structure that was simultaneously physical, providing the geometric arena for motion, and theological, manifesting God's omnipresence. Natural philosophy and theology weren't separate domains, but different approaches to understanding the same divine reality. This unified vision, where physics reveals theological truth and theology grounds physical concepts, is perhaps most foreign to modern readers. We've learned to compartmentalize, to keep science and religion in separate boxes. Newton refused this separation. His physics and his theology formed an integrated whole, and many of the tensions in his physics arose precisely because he was trying to satisfy both empirical and theological demands simultaneously.
Understanding absolute space as God's omnipresence helps explain why Newton was so resistant to Cartesian mechanism. Descartes' identification of matter with extension eliminated any ontological difference between material bodies and space itself. It was all just extended substance. But if space is God's omnipresence, then matter cannot be identical with space. Bodies must be something distinct that exists in space without being space. This required Newton to conceive matter differently, as endowed with properties, mass, inertia, force, that weren't reducible to pure extension. This conception of matter as more than geometric extension opened the door for Newton's forces. If matter is just extension, only contact forces make sense. Bodies can only affect each other by touching, by geometric interaction. But if matter has properties beyond extension, other kinds of forces become conceivable. Gravity, operating across empty space without contact, makes no sense in Cartesian physics, but is at least possible in Newtonian physics, where matter has active powers. The theological grounding also explains Newton's vehement opposition to atheistic interpretations of his physics. When Leibniz accused Newton's absolute space of making God into a spatial being who needs space to exist, Newton, through Clarke, responded indignantly. God doesn't need space. Space exists because God is omnipresent. The structure of space manifests divine attributes. To understand the universe is to understand something about God's nature. This wasn't natural theology in the weak sense of inferring God's existence from design. It was natural theology in a much stronger sense. Physics as direct investigation of divine attributes. Mathematical laws as expressions of divine rationality. Space itself as manifestation of divine omnipresence. Nature didn't just point to God, it directly exhibited God's continuous activity. Contemporary readers may wonder why Newton didn't simply state this theological foundation explicitly in the Principia, rather than burying it in cautious hints and later defending it through Clarke's correspondence with Leibniz. The answer lies in Newton's acute awareness of how theological claims could undermine his physics' credibility. He'd seen Descartes' system dismissed partly because its reliance on God to conserve motion seemed like special pleading. He knew that mixing physics and theology too explicitly would invite the charge that his physics was merely disguised theology, depending on undemonstrable religious premises rather than mathematical demonstration from phenomena. So Newton adopted a strategic rhetoric. Present the physics mathematically without explicit theological grounding, demonstrate its empirical success overwhelmingly, then add theological interpretation carefully in scholia and queries that could be read as philosophical speculation rather than necessary foundations. This strategy succeeded so well that most readers accepted the physics while remaining unaware of or ignoring the theological framework. But the price of this success was the eventual secularization of Newtonian physics, the transformation of Newton's theologically grounded natural philosophy into the mechanistic, secular physics of the Enlightenment. Later Newtonians kept the mathematics and the methodology while discarding or downplaying the theological foundations. Absolute space became an abstract mathematical entity rather than God's omnipresence. This made the physics more acceptable to diverse audiences, but also more philosophically vulnerable. Without the theological grounding, absolute space's ontological status became increasingly problematic. The concept of absolute space thus perfectly exemplifies Newton's genius and his legacy's complexity. It was simultaneously a brilliant physical insight, acceleration and rotation are absolute; a problematic metaphysical commitment, space as independently existing entity; philosophical development, prompting responses from Leibniz, Berkeley, Kant, and ultimately Einstein. Understanding this complexity is essential for grasping Newton's actual achievement rather than the simplified myth. He didn't create a purely secular mechanistic physics. He created a theologically grounded physics whose theological foundations were gradually obscured and then forgotten, leaving conceptual tensions that drove centuries of philosophical and scientific development. Bridging rationalism and empiricism, Newton's methodology. One of Newton's most profound legacies, perhaps more important than any specific physical law, was his methodological synthesis. He emerged at a moment when European philosophy was divided into two seemingly incompatible camps: continental rationalism, exemplified by Descartes, Spinoza, and Leibniz, and British empiricism, exemplified by Bacon, Locke, and later Hume. Newton created a middle way, a synthesis that combined rationalism's mathematical rigor with empiricism's experimental foundation. This synthesis became the template for modern scientific method. To understand Newton's achievement, we must first grasp what separated rationalists and empiricists and why bridging them mattered. The rationalist position. Rationalists believed that genuine knowledge must be certain, necessary, and universal, like mathematical truths. Mere empirical observation, they argued, could never provide such knowledge because 1. The senses can deceive us, perceptual illusions, dreams. 2. Sensory experience varies between observers, subjectivity. 3. Inductive generalization from particular observations never yields logical certainty, the problem Hume would later make famous. 4. Necessary truths, like mathematical principles, can't be derived from contingent empirical facts. Therefore, rationalists concluded true knowledge must be derived from clear and distinct ideas grasped by reason alone, using deductive logic to derive conclusions from self-evident axioms. Descartes' physics exemplified this method. He claimed to deduce the laws of nature from his metaphysics. Because God is perfect and immutable, God must preserve the same total quantity of motion in the universe. From this principle, plus geometric reasoning about how motion is transferred through contact, Descartes derived his laws of impact and his vortex theory of planetary motion. The physics was meant to follow deductively from metaphysical first principles. The empiricist position. Empiricists argued that all genuine knowledge derives ultimately from sensory experience. Reason alone, without empirical input, can never tell us about the actual world because 1. Reason can only make explicit what's implicit in our premises, deductive validity. But where do premises come from if not experience? 2. Mathematical knowledge is merely about relationships between ideas, not about actual existence. 3. Necessary truths like mathematics and logic are empty. They don't tell us what actually exists. 4. Knowledge of nature must be grounded in observation and experiment, not armchair speculation. Francis Bacon had articulated this vision powerfully. Genuine natural philosophy must proceed through careful observation, systematic experiment, and cautious generalization. Rather than starting from speculative first principles and deducing consequences, we should start from phenomena and inductively work toward principles. But empiricism faced its own severe problems, which Hume would later make devastatingly clear. 1. How do we justify induction, inferring general principles from particular observations? No amount of observations logically entails that the next case will resemble past cases. 2. How do we move from observable phenomena to unobservable causes? We observe regularities, but not necessities. 3. How do we achieve the certainty and precision that mathematics provides? Empirical knowledge always remains provisional and approximate. Newton's synthesis preserved strengths of both approaches while partly evading their weaknesses. From rationalism, Newton took 1. Mathematical form. Physical laws should be expressed mathematically, providing precision and enabling rigorous derivation. 2. Deductive structure. From a few fundamental principles, derive testable consequences through mathematical reasoning. 3. Unity. Seek unified principles that explain diverse phenomena, like universal gravitation explaining both terrestrial and celestial motion. 4. Necessity. Physical laws have a necessary character. They're not merely observed regularities, but express how nature must behave. From empiricism, Newton took 1. Experimental foundation. Principles must be constrained by observation and experiment, not derived from pure speculation. 2. Phenomena first. Begin with careful observation of what actually happens, not what reason says must happen. 3. Inductive inference. Generalize cautiously from observed cases to general principles. 4. Testability. Theories must make predictions that can be confirmed or falsified by observation. The result was something new, a mathematical experimental method that combined deductive rigor with empirical constraint. Newton's actual procedure in the Principia exemplifies this synthesis. Phase 1. Mathematical hypotheticals. In Books 1, Newton explored mathematical relationships hypothetically. If a body moves under a central force inversely proportional to the square of distance, then it will move in a conic section. This section is pure mathematical reasoning, deriving consequences from assumptions without yet claiming those assumptions describe actual nature. Phase 2. Empirical phenomena. In Book 3, Newton listed phenomena, carefully established empirical facts. The moons of Jupiter obey Kepler's third law, Saturn's moons obey it, our moon obeys it, the planets obey it. These aren't mere casual observations, but precise measurements establishing quantitative relationships. Phase 3. Rules of reasoning. Newton articulated explicit rules for moving from phenomena to principles, discussed in detail in our next chapter. These rules attempted to justify inductive inference, how we can legitimately generalize from observations. Phase 4. Inference to universal principles. Using the phenomena and rules, Newton inferred universal gravitation. All bodies attract all other bodies with force proportional to their masses and inversely proportional to the square of distance. This principle unified terrestrial gravity, explaining falling bodies and projectile motion, with celestial gravity, explaining planetary orbits and lunar motion.
Phase 5. Further predictions. From universal gravitation, Newton derived additional predictions. Tides should have specific patterns caused by moons and suns' differential gravity. Earth should be oblate, bulging at equator due to rotation. Comets should move in very elongated ellipses around the sun. Planetary orbits should show small perturbations due to mutual gravitational influences. Phase 6. Empirical confirmation. These predictions were confirmed by observation, providing strong evidence for the theory's truth. This procedure was revolutionary because it showed how mathematical physics could be empirically grounded without sacrificing rigor. The mathematics provided deductive certainty within the system. Given Newton's laws, specific motions followed necessarily. But the laws themselves were constrained by empirical phenomena, not derived from pure reason. This resolved, or appeared to resolve, the rationalist-empiricist tension. Against pure rationalism. You can't derive physics from metaphysical first principles alone. Nature's actual behavior must constrain theory. Against pure empiricism.
You can't build physics from scattered observations alone. Mathematical principles are needed to organize and unify phenomena. The synthesis. Mathematical principles derived from and constrained by empirical observations, then extended through mathematical reasoning to make novel predictions. But Newton's synthesis also contained unresolved tensions that philosophers quickly identified. The induction problem. Newton's rules of reasoning attempted to justify inductive inference, generalizing from observed cases to universal principles. But do these rules actually justify induction logically? Rule 3 stated, "Qualities of bodies that cannot be intended and remitted and that belong to all bodies on which experiments can be made should be taken as qualities of all bodies universally." This sounds reasonable, but is it logically valid? Hume would later argue that no amount of observed cases logically entails that unobserved cases will resemble them. The unobservable absolute. Newton needed absolute space for his physics, but absolute space isn't directly observable. We only ever observe relative positions and motions. This seemed to violate his empiricist rhetoric about deriving physics from phenomena. Berkeley and Leibniz exploited this tension. If your methodology demands empirical grounding, how can you posit unobservable absolutes? The force problem. Gravity itself raised methodological issues. We never observe gravitational force directly, we observe motions and infer force as their cause. But how do we justify inferring unobservable causes from observable effects? Hume would make this problem central to his skeptical philosophy. The certainty question. Newton's physics achieved remarkable empirical success, but did this make it certain or merely highly confirmed? Rationalists wanted necessity and certainty. Newton's method provided only high probability. Later observations might disconfirm current theories, as relativity would eventually modify Newton's laws. The hypothesis problem. Newton famously declared, "Hypothese non fingo," I frame no hypotheses. But what exactly counted as hypothesis versus legitimate inference? Newton treated universal gravitation as demonstrated from phenomena, not merely hypothesized. But critics wondered, isn't positing an invisible force acting across empty space exactly the kind of speculation that should count as hypothesis? These tensions made Newton's methodology philosophically productive. It was clear enough to guide successful research, but ambiguous enough to prompt philosophical investigation. Different thinkers interpreted Newton's method differently, leading to distinct philosophical traditions. Locke's interpretation. John Locke, who discussed methodology with Newton, developed an empiricist epistemology that treated Newtonian physics as the paradigm. For Locke, knowledge came through experience, sensation and reflection, and Newton had shown how careful observation plus mathematical reasoning could yield genuine knowledge of nature. But Locke also recognized limits. We might discover laws that nature follows without ever understanding the underlying real essences or mechanisms. This modest empiricism accepted that science might describe without fully explaining. Berkeley's critique. George Berkeley accepted Newton's physics as predictively successful, but rejected its realist metaphysics. For Berkeley, all we ever observe are patterns in our experiences. We never observe material substance or absolute space or gravitational force. These are unnecessary theoretical entities. Berkeley proposed an instrumentalist reading. Newtonian physics is a useful instrument for predicting phenomena, not a description of unobservable reality behind phenomena. Hume's radicalization. David Hume took Newton's empiricism more seriously than Newton himself. Hume asked, if all knowledge must be grounded in experience, and experience only reveals constant conjunction, one event regularly following another, never necessary connection, then how can we know natural laws are truly necessary? Hume concluded we can't. Causation itself is merely psychological expectation based on habit, not objective necessity we observe in nature. This undercut Newton's claim that his laws expressed nature's necessary structure. Kant's synthesis. Immanuel Kant developed his entire critical philosophy largely in response to tensions in Newtonian method. Kant asked, how is Newton's mathematical physics possible? If Hume is right that experience never gives us necessity, but Newton's laws are both universal necessary and yet known through experience, how is this possible? Kant's revolutionary answer, the necessary structure comes not from nature itself, but from the way our minds structure experience. Space, time, and causality are a priori forms that minds impose, making mathematical physics possible, but limiting it to the phenomenal realm, things as they appear, rather than the noumenal realm, things as they are in themselves. Each philosophical response attempted to resolve or explain tensions in Newton's methodology. The fact that such diverse philosophies emerged from engagement with Newton testifies to his method's richness and ambiguity. Newton himself seemed relatively unconcerned with philosophical niceties. His methodological statements were meant to defend his physics against specific objections, not to develop a comprehensive epistemology. When he said hypotheses non fingo, he meant, I'm not speculating about mechanisms I can't demonstrate. I'm sticking to what I can derive from phenomena. When he articulated rules of reasoning, he meant, here's how I'm justifying my inductive inferences. If you disagree, provide better rules. This pragmatic attitude frustrated philosophers who wanted clearer methodological foundations, but it exemplified Newton's genius. He recognized that methodology must serve research, not the reverse. Rather than first developing a complete epistemology and then doing physics within its constraints, Newton did physics first, articulating methodology as needed to defend his practice. This put philosophy in a responsive position. Philosophers had to deal with Newton's successful but philosophically puzzling physics, rather than dismissing it for violating prior methodological commitments. The result was a productive reversal. Instead of philosophy legislating what science could legitimately do, science's success forced philosophy to adapt. When Newton's physics worked despite seeming to violate proper method, by positing action at a distance, by inferring unobservables, by generalizing beyond observed cases, philosophers couldn't simply dismiss it. They had to explain how such knowledge was possible, or reinterpret what Newton had actually accomplished, or revise their methodological standards. This pattern continues in modern philosophy of science. Scientific revolutions, quantum mechanics, relativity, evolutionary biology, consistently outpace philosophical frameworks meant to constrain them. Philosophers scramble to explain how revolutionary science is possible, often modifying epistemology to accommodate scientific practice rather than judging practice by pre-existing epistemology. Newton's synthesis thus established not just a method, but a relationship between science and philosophy. Science pursues knowledge through whatever methods work empirically. Philosophy attempts retrospectively to understand and justify those methods. This can seem to reduce philosophy to second-order commentary, but it also makes philosophy essential. Successful scientific practice needs philosophical interpretation to be properly understood, taught, and extended to new domains.
The rules of scientific reasoning. Perhaps no phrase in the history of science has been more quoted, more misunderstood, and more philosophically significant than Newton's declaration, hypothesis non fingo, usually translated as I frame no hypotheses or I do not feign hypotheses. This phrase appears in the General Scholium, added to the second edition of the Principia, 1713, and it represents Newton's explicit methodological stance, his defense against critics who charged that his physics was insufficiently explanatory or too speculative. To understand what Newton meant and why it mattered, we must place this declaration in context.
By 1713, when the second edition appeared, Newton's physics had achieved remarkable empirical success. The Principia's first edition, 1687, had demonstrated that universal gravitation explained planetary motion, the moon's complex movements, tides, comets, and much else. But this success came at a philosophical cost. Newton couldn't explain how gravity worked. He described it mathematically, force proportional to masses, inversely proportional to distance squared, but provided no mechanical explanation for how this force was transmitted across empty space. This made many natural philosophers, especially continental followers of Descartes, deeply uncomfortable. For them, proper natural philosophy meant reducing all phenomena to matter in motion, explaining everything through geometric principles and contact forces. Newton's gravity seemed like a throwback to medieval occult qualities, mysterious powers that bodies possessed without any comprehensible mechanism. Leibniz, Newton's great rival and critic, made this objection explicit. Gravity was a perpetual miracle, an inexplicable action at a distance that violated proper mechanical philosophy. Christian Huygens, despite recognizing the Principia's mathematical brilliance, insisted that any acceptable physical theory must explain phenomena through mechanical causes, not just mathematical description. Newton was stung by these criticisms, but also recognized them as philosophically serious. His famous declaration must be understood as a response. I have not as yet been able to deduce from phenomena the reason for these properties of gravity, and I do not feign hypotheses. For whatever is not deduced from the phenomena must be called a hypothesis. And hypotheses, whether metaphysical or physical, or based on occult qualities or mechanical, have no place in experimental philosophy. In this experimental philosophy, propositions are deduced from the phenomena and are made general by induction. This passage makes several crucial distinctions. Demonstrated knowledge versus speculation. Newton distinguished sharply between what he could demonstrate mathematically from empirical phenomena, that gravity follows an inverse square law, that this principle explains observed motions, and what he could only speculate about, how gravity works, what transmits it, why it exists. Hypothesis versus theory. Newton used hypothesis as a term of criticism, not approval. A hypothesis, in his terminology, was a speculative proposal that couldn't be demonstrated from phenomena, whether mechanical explanations for gravity, or metaphysical theories about matter's nature, or claims about occult qualities. These weren't necessarily false, but they went beyond what evidence could establish, and therefore had no place in experimental philosophy. Induction from phenomena. Newton claimed his laws were deduced from phenomena and made general by induction. This process began with careful observation, phenomena, proceeded to mathematical description, laws, and extended through generalization, induction, to universal principles. At each stage, the connection to empirical evidence remained clear and demonstratable. But what exactly did Newton mean by saying he didn't feign hypotheses? The Latin verb fingo, to shape, form, fashion, feign, pretend, has connotations of artificiality, making something up rather than discovering it. Newton's point wasn't that he made no conjectures or theoretical proposals at all. He made plenty. Rather, he distinguished between 1. Legitimate theoretical principles that were either directly observed in phenomena, or derived mathematically from observed phenomena, or generalized inductively from observed cases following explicit rules. 2. Illegitimate hypotheses that were speculative mechanisms with no empirical foundation, or metaphysical assumptions treated as demonstrated truth, or explanatory proposals that went beyond what phenomena required. Universal gravitation was legitimate because it was derived from phenomena, Kepler's laws, lunar motion, pendulum experiments, through mathematical analysis and inductive generalization. The vortex theory of planetary motion, Descartes' proposal that planets were carried by swirling material fluids, was illegitimate because it couldn't account for observed phenomena and was proposed speculatively. This distinction became clearer in Newton's Rules of Reasoning in Philosophy, which he included in Book 3 of the Principia to justify his inductive inferences. These rules evolved across editions. 4 rules in the second edition, 1713, with more elaborate explanations. They represent Newton's explicit attempt to establish methodological principles for legitimate scientific inference. Rule 1. We are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. This rule of parsimony, often called Occam's razor, demanded economy in explanations. Don't multiply causes unnecessarily. If one cause suffices to explain phenomena, don't invoke multiple causes. Newton applied this to argue that one force, universal gravitation, explained both terrestrial and celestial phenomena, so we shouldn't posit separate causes for falling apples and orbiting moons. Rule 2. Therefore, to the same natural effects, we must, as far as possible, assign the same causes. This rule of uniformity extended parsimony. Similar effects should be attributed to similar causes unless evidence suggests otherwise. Falling bodies on Earth and falling bodies on the Moon show similar mathematical relationships, so they should be explained by the same gravitational principle. Rule 3. The qualities of bodies which admit neither intensification nor remission of degrees, and which are found to belong to all bodies within the reach of our experiments, are to be esteemed the universal qualities of all bodies whatsoever. This rule justified inductive generalization, from observed to unobserved cases. Extension, hardness, impenetrability, qualities observed in all bodies we can examine and which can't be increased or decreased, can be generalized to all bodies universally. Newton added gravity to this list. Since every body we've tested exhibits gravitational attraction proportional to its mass, we can generalize that all bodies possess this quality. Rule 4, added in the second edition. In experimental philosophy, we are to look upon propositions inferred by general induction from phenomena as accurately or very nearly true, notwithstanding any contrary hypotheses that may be imagined, till such time as other phenomena occur, by which they may either be made more accurate or liable to exceptions. This rule addressed the problem of induction directly. It acknowledged that inductive inferences aren't logically certain, future observations might require revision, but it insisted that such inferences should be treated as established truth until contrary evidence appears, not as mere speculations equally balanced against alternative hypotheses. These rules were revolutionary but also philosophically problematic. They attempted to codify legitimate scientific reasoning, providing explicit principles for moving from observations to general laws. But they raised deep questions. The induction puzzle. Do these rules actually justify induction? Rule 3 says we can generalize observed properties to all bodies. But why? What logical principle entitles us to infer that unobserved cases will resemble observed ones? Newton provided no answer, beyond asserting this as a methodological rule. Hume would later argue that no such justification exists. Induction is psychologically compelling, but logically unjustified. The circularity problem. Rule 3 includes gravity as a universal quality because it's found in all tested bodies. But Newton used this rule to justify inferring universal gravitation in the first place. This seems circular. We infer universal gravitation from Rule 3, but we justify including gravity in Rule 3 because we've inferred universal gravitation. The parsimony question. Rule 1 demands that we admit no more causes than necessary. But how do we determine what's necessary? Before Newton, one might argue that terrestrial and celestial motions obviously require different explanations because they're so different in character. Newton's unification was revolutionary precisely because it reduced two causes to one, but only in retrospect do we see this as parsimonious rather than implausible. The theory dependence problem. Rule 2 says similar effects should have similar causes. But what counts as similar? A falling apple and an orbiting moon don't appear similar until you describe them both mathematically in terms of accelerations toward a central body. The judgment of similarity depends on prior theoretical commitments about what features matter. Despite these philosophical problems, Newton's rules became influential templates for scientific reasoning. They articulated, even if they didn't fully justify, practices that seemed to work. Look for unified explanations rather than multiplying hypotheses. Generalize cautiously from well-established observations. Treat empirically successful theories as true until contrary evidence appears. Distinguish demonstrated conclusions from speculative hypotheses. The hypotheses non-fingo stance also had immediate strategic value for Newton. It let him avoid defending the mechanism of gravity while insisting on gravity's reality and mathematical description. When critics complained that he hadn't explained how gravity works, Newton could respond, "I don't need to. I've demonstrated that it follows an inverse square law and that this law explains phenomena. Whether gravity is transmitted through material medium or through spiritual action or through some other mechanism, that's hypothesis, and I don't feign hypotheses. I stick to what I can demonstrate." What was Newton looking for? Several interrelated goals. Active principles in matter. Mechanical philosophy reduced all causation to matter in motion through contact. But this couldn't explain chemical affinity. Why gold doesn't mix with mercury but readily dissolves in aqua regia. Why certain substances combine while others don't. Newton believed there must be active forces operating at microscopic scales. Attractions and repulsions between particles explaining selective combination. This wasn't mystical speculation, but an attempt to extend his gravitational insight. If bodies attract gravitationally at large scales, perhaps other forces operate at small scales. Alchemy provided the experimental domain for investigating these forces. Vegetable and metallic generation. Alchemical tradition held that metals grow in the earth through slow processes, gradually maturing from base metals toward perfection, gold. Newton took this seriously as a natural hypothesis. Perhaps metals do undergo transformations over time through internal principles. If so, understanding and accelerating these natural processes might enable transmutation, not through magic, but through comprehending nature's own methods. The universal spirit. Many alchemical texts referred to a universal spirit or spirit of the world, an active principle pervading all matter, mediating transformations, connecting all things. Newton interpreted this not as supernatural, but as a kind of universal force or medium, perhaps the same ether that might transmit gravity and light. The philosopher's stone. The legendary substance that could transmute base metals to gold and confer immortality was, for serious alchemists, not a magical object, but the perfection of chemical knowledge. A substance or process that would demonstrate complete understanding of matter's transformability. Newton may have sought this not from greed, but as the ultimate test of whether matter's principles could be fully comprehended. Connections to physics. Newton's alchemy wasn't separate from his physics, but deeply connected. Forces beyond mechanism. Both alchemy and gravity required forces beyond simple contact mechanics. If gravitation acted at a distance at large scales, perhaps chemical forces acted at distance at small scales. Alchemy provided evidence that purely mechanical philosophy was insufficient. The structure of matter. Newton's corpuscular theory of matter, mentioned in the Principia and Optics, suggested that matter consists of hard, massy, indivisible particles with various forces acting between them. Alchemy investigated how these particles combined and transformed. The ether problem. Newton's varying attitudes toward ether, sometimes requiring it to transmit forces, sometimes suggesting forces act through empty space, connected to alchemical ideas of universal medium or spirit pervading matter. Query 31. In the Optics, Newton posed a long query, really a treatise, suggesting that all natural phenomenon might result from attractive and repulsive forces between particles, that chemical reactions might be explained by these forces, that even biological processes might reduce to force-based mechanisms. This directly reflected his alchemical investigations. The Mercury antimony star. One dramatic incident illustrates Newton's alchemical work's seriousness and danger. In the early 1690s, Newton suffered a mental breakdown. Sleeplessness, paranoia, depression, bizarre behavior, including accusatory letters to friends. The cause remained mystery until recent analysis suggested mercury poisoning from his alchemical work. Newton frequently worked with mercury, heating it with various substances, a process that releases toxic fumes. His symptoms matched mercury poisoning. Hair samples preserved from his later years show elevated mercury levels. The breakdown may have been literally toxic consequence of experimental investigations. This suggests how seriously Newton took alchemical work. He risked his health, possibly his life, conducting experiments. This wasn't casual hobby, but passionate pursuit of knowledge, dangerous enough to damage the mind that had produced the Principia. Why Newton failed. Newton's alchemical quest ultimately failed. He didn't transmute base metals to gold, didn't discover the philosopher's stone, didn't find the universal spirit. Why? Wrong framework. However sophisticated, alchemetical theory was fundamentally wrong about matter's nature. Transmutation isn't impossible. Nuclear physics can transform elements, but it requires understanding atomic structure that was 2 centuries away. Chemical combination depends on electron configurations, not mysterious affinities or active principles. Inadequate techniques. 17th century apparatus and methods couldn't isolate pure elements, measure precisely enough, control conditions carefully enough to discover genuine chemical principles. Newton was trying to understand chemistry before chemistry's conceptual foundations existed. Misleading texts. Alchemical literature was deliberately obscure, mixing genuine observations with symbolic allegory, hiding practical recipes in fantastic narratives. Even genius couldn't reliably extract truth from this confused mixture. Theoretical dead end. The active principles Newton sought, forces explaining chemical affinity, do exist, but they're electromagnetic forces between atoms' electron clouds, a level of analysis requiring atomic theory, quantum mechanics, concepts utterly unavailable in Newton's time. Yet Newton's alchemical failure was productive failure. It kept him engaged with matter's properties and transformations, maintaining awareness that mechanical philosophy was incomplete. It reinforced his conviction that nature contained forces beyond contact mechanics. It drove his speculations about ether, active principles, and attractive forces that connected to his physics. The posthumous suppression. After Newton's death, his alchemical manuscripts embarrassed his scientific heirs. The Enlightenment wanted Newton as rationalist hero, not mystical alchemist.
His chemical papers were deemed unworthy of the great man, evidence of temporary aberration. For 2 centuries, Newton's alchemy remained largely hidden. His reputation rested entirely on the Principia, optics, and mathematical work. The alchemical Newton, obsessive experimenter seeking nature's active principles through dangerous chemical investigations, was suppressed, mentioned only to be dismissed as regrettable lapse. Only in the mid-20th century, when scholars finally examined Newton's full manuscript collection systematically, did the scope and seriousness of his alchemical work become clear. The economist John Maynard Keynes, who purchased many Newton manuscripts, proclaimed in a famous lecture that Newton was not the first of the Age of Reason, he was the last of the magicians. This judgment, though catchy, was also misleading. Newton wasn't reverting to medieval magic. He was trying to extend natural philosophy beyond mechanism's limits, using every available tool, including alchemy. Hates the simple narrative of scientific progress. He wasn't purely rational scientific thinker leaving behind medieval superstition. He was a figure straddling 2 eras, bringing rigorous mathematical method to bear on both the tractable, celestial mechanics, and the intractable, chemical transmutation, achieving revolutionary success in one domain while failing in another. Understanding this complexity is essential for grasping how science actually develops, not through pure rationality alone, not by geniuses transcending their time's limitations, but through passionate engagement with problems, using whatever tools and frameworks available, sometimes succeeding spectacularly and sometimes failing productively, with even failures driving understanding forward by revealing what current frameworks can't explain. Recovering ancient wisdom, Newton's Prisca Theologia.
Among Newton's less known but deeply important pursuits was his attempt to recover ancient wisdom, the belief that early civilizations, closer to divine revelation, possessed true knowledge that was later corrupted or lost. This project, which occupied Newton especially in his later years, was not antiquarian curiosity, but a systematic effort to reconstruct the original truths of religion, natural philosophy, and history before they were distorted by false interpretations and institutional corruption. The Prisca Theologia tradition. Newton's work in this area connected to a long Renaissance tradition called Prisca Theologia, ancient theology, or Philosophia perennis, perennial philosophy, the belief that certain fundamental truths about God, nature, and morality had been revealed to the earliest humans and preserved in various ancient traditions. This tradition held that original revelation, God revealed truth to the biblical patriarchs, Adam, Noah, Abraham, Moses, who passed it to their descendants. This revelation included both religious truth, monotheism, moral law, and natural knowledge, astronomy, mathematics. Corruption and preservation. Over time, this original wisdom was corrupted by idolatry, superstition, and philosophical error. but fragments survived in various ancient traditions: Egyptian mysteries, Pythagorean philosophy, Hermetic texts, biblical prophecy. Recovery project. Careful study could recover original truth by comparing sources, identifying commonalities, reconstructing what must have been the uncorrupted original. This wasn't fringe belief, but respectable scholarship in the Renaissance and early modern period. Thinkers from Marsilio Ficino to Athanasius Kircher pursued Prisca Theologia, seeking to show that pagan philosophy at its best agreed with biblical revelation, because both drew on original divine truth. Newton brought his characteristic rigor and obsessiveness to this project, producing thousands of pages of historical research, linguistic analysis, and astronomical calculation aimed at reconstructing ancient wisdom. Ancient monotheism. Newton's theological research sought to prove that original Christianity, and indeed original religion going back to Noah, was strictly monotheistic, worshipping one God without the later Trinitarian complications. He argued, biblical evidence. Careful reading of Scripture showed that the earliest texts taught one God, with Jesus as God's unique Son, but not co-eternal or co-equal. Trinitarian language in the Bible was either misinterpreted or later interpolation. Historical corruption. The Trinity was imposed by church councils in the 4th century, especially Nicaea in 325 CE, for political reasons, supported by Emperor Constantine, who wanted religious unity to strengthen his empire. The original teaching was suppressed and dissenters persecuted. Ancient parallels. Even pagan philosophers, Pythagoras, Socrates, Plato, taught monotheism when properly understood. Their references to multiple divine beings were either symbolic or referred to subordinate spiritual entities, not true divinity. This research supported Newton's secret anti-Trinitarianism. By showing that the Trinity was later corruption, he vindicated his own rejection of it. He wasn't heretic abandoning true Christianity, but recovering original truth from institutional distortion. Ancient heliocentrism. Newton also pursued the startling claim that ancient philosophers knew the heliocentric system, that Earth and planets orbit the Sun, long before Copernicus supposedly discovered it in the 16th century. His evidence. Pythagorean fire. Ancient sources attributed to Pythagoras and his followers the doctrine that celestial bodies orbit a central fire. Newton interpreted this not as mystical symbolism, but as coded reference to heliocentrism, the sun as central fire around which planets move. Temple of Vesta. The Vestal virgins in Rome tended a sacred fire that must never be extinguished. Newton suggested this perpetual fire symbolized the sun at the cosmic center, preserving memory of ancient heliocentric knowledge. Egyptian astronomy. Newton believed ancient Egyptian priests possessed advanced astronomical knowledge, including heliocentrism, which they encoded in religious symbols and architectural designs.
Certain cryptic passages in Plato and other philosophers, when properly interpreted, revealed heliocentric understanding disguised in mythological language to avoid persecution by authorities committed to geocentrism. Why would ancients conceal this knowledge? Newton suggested several reasons. Religious/political, geocentrism supported anthropocentric worldview and terrestrial political authority. Heliocentrism was threatening, so true astronomers communicated it only to initiates through coded language. Gradual loss. As civilizations declined and knowledge became corrupted by Aristotelian philosophy, the original truth was forgotten except in fragmentary, misunderstood forms. Intentional obscurity. Ancient philosophers deliberately wrote obscurely, following Pythagorean tradition of restricting advanced knowledge to worthy students, preventing masses from misusing or corrupting it. This claim wasn't entirely absurd. Aristarchus of Samos, 3rd century BCE, did propose heliocentrism, though the idea wasn't generally accepted. Newton may have been overinterpreting scattered evidence, but he wasn't inventing it entirely. Chronology and astronomical dating. Newton's most extensive historical work was his attempt to establish correct chronology for ancient history using astronomical methods. This produced two major works, Chronology of Ancient Kingdoms Amended, published posthumously, and related manuscripts. His method: astronomical phenomena. Ancient texts mentioned eclipses, planetary conjunctions, and other datable astronomical events. By calculating when these occurred, Newton could establish absolute dates for events mentioned in texts. Precession of the equinoxes. Earth's axis precesses changes orientation over 26,000-year cycles. Ancient astronomical observations could be dated by calculating precession's effects on observed star positions. Generation lengths. By analyzing genealogies and assuming realistic generation lengths, how long between ancestors and descendants, Newton attempted to establish timelines for ancient dynasties. Cross-cultural comparison. By comparing Egyptian, Greek, Persian, and biblical chronologies and identifying same events described differently, Newton tried to create a unified timeline. His conclusion: standard chronologies were wrong. Ancient history was shorter than traditionally believed. Events dated centuries apart actually occurred closer together. Egyptian dynasties overlapped rather than succeeding each other. This challenged accepted scholarship but followed from Newton's rigorous approach: use objective methods, astronomical calculation, rather than accepting traditional authorities uncritically. The Temple of Solomon. Newton devoted extensive attention to reconstructing Solomon's temple in Jerusalem, producing detailed architectural diagrams and measurements. Why? Religious significance. The temple was God's dwelling place, designed according to divine specifications. Its proportions might encode sacred geometry, divine ratios, fundamental truths. Scientific symbolism. Newton believed the temple's design symbolized cosmic structure. Its courts represented planetary spheres, its measurements encoded astronomical ratios, its architecture taught heliocentric system to initiates. Prophetic importance. Biblical prophecies described the temple's future destruction and restoration. Accurate reconstruction was needed to understand prophecy correctly. Ancient wisdom. Solomon possessed divine wisdom, including natural knowledge. The temple's design might preserve this wisdom for those who could decode it. Newton's temple reconstructions were technically sophisticated, showing architectural knowledge and geometric skill. But the symbolic interpretations were highly speculative. He read heliocentric astronomy and Pythagorean mathematics into dimensions and proportions that might have had purely practical or aesthetic purposes. Prophecy and history. Newton's chronological and prophetic studies aimed to understand God's historical plan. He believed biblical prophecy encoded the pattern of history from ancient times through the end days. Proper interpretation required. Symbolic decoding. Prophetic visions used symbolic language: beasts representing empires, horns representing rulers, women representing churches or nations. Historical knowledge. Prophecy described actual historical events symbolically.
Understanding prophecy required accurate history. Conversely, prophecy could correct historical errors. Mathematical calculation. Some prophecies included time periods, 70 weeks, 42 months, etc.
Converting these to actual time required mathematical analysis of prophetic chronology. Newton identified several prophetic timelines, calculating that certain prophecies had been fulfilled in church history, particularly the rise of papal authority as the prophesied apostasy, while others awaited future fulfillment. His famous calculation that the world wouldn't end before 2060 wasn't date-setting. He condemned setting exact dates, but establishing a minimum. Based on prophetic timelines from Daniel and Revelation, the end times couldn't arrive before roughly this date. This was meant to counter apocalyptic enthusiasts who predicted imminent ends. Why recover ancient wisdom? What motivated Newton's extensive historical research? Several interrelated goals. Religious truth. Recovering original monotheism vindicated his anti-Trinitarian conviction and showed true Christianity from institutional corruption. Natural philosophy. If ancients knew heliocentrism, it validated Newton's own astronomical work as recovery rather than innovation. He wasn't contradicting tradition, but restoring it. Unified knowledge. Showing that religion, natural philosophy, and history all pointed to the same truths: one God, rational cosmic order, providential history, unified knowledge rather than dividing it into separate domains. Divine plan. Understanding prophecy and chronology revealed God's purposes in history, showing that history wasn't random but followed divine plan. Intellectual authority. Claiming ancient authorization for his ideas gave them additional weight. He wasn't revolutionary upstart but faithful restorer of ancient truth. Methodology and problems. Newton approached historical research with the same rigor as natural philosophy. Source criticism. He compared different versions of ancient texts, identified interpolations, attempted to establish original readings. Systematic analysis. He created detailed chronological tables, cross-referenced sources, looked for patterns and consistencies. Mathematical methods. He used astronomical calculation, geometric analysis, and numerical patterns to establish dates and decode symbols. But his historical work had severe limitations. Confirmation bias. Newton tended to find in ancient texts what he was looking for: monotheism, heliocentrism, coded natural philosophy, often by forcing interpretations. Insufficient evidence. Many of his conclusions rested on fragmentary evidence, ambiguous passages, and creative readings that alternative interpretations could challenge. Anachronism. He sometimes projected his own concerns onto ancient authors, assuming they were addressing questions, Trinity, heliocentrism, that might not have been their primary concerns. Symbolic overinterpretation. His tendency to see everything as encoding deeper meaning led to finding significance in coincidences and reading complex systems into simple observations. Reception and legacy. During Newton's lifetime, his historical research was less influential than his natural philosophy. The chronology, published after his death, received mixed reviews. Some scholars found it intriguing, others criticized its speculative leaps. His refusal to publish theological research meant those works had little contemporary impact. Only scholars who examined his papers after death discovered the extent of his theological obsessions. Modern historians take Newton's historical research seriously, not because his conclusions were correct, mostly they weren't, but because they reveal his unified intellectual vision. For Newton, recovering ancient wisdom, establishing accurate chronology, decoding prophecy, and discovering natural laws were all aspects of one project: understanding God's nature and God's plan through every available source. This historical research also shows Newton's characteristic approach: take nothing on authority, examine sources critically, use mathematical and analytical methods, reconstruct truth systematically from evidence.
The same methodology that succeeded brilliantly in physics failed in ancient history because the evidence was insufficient and the framework, Prispeciologia, was ultimately wrong. But the approach, rigorous, systematic, refusing to accept traditional answers uncritically, was consistent. The unity of Newton's vision. Understanding Newton's ancient wisdom project is essential for grasping his actual worldview. Modern readers see his physics, theology, and historical research as separate domains. For Newton, they were unified. Natural philosophy studied God's creative wisdom through nature. Theology studied God's moral nature and redemptive plan through Scripture. Prophecy studied God's historical providence through biblical visions. Chronology studied the actual history through which God's plan unfolded. Ancient wisdom recovered original truths before corruption. All paths led to the same destination, understanding the one true God who created nature according to mathematical laws, revealed truth to the patriarchs, guided history according to prophetic plan, and would ultimately restore pure religion and complete knowledge. This unified vision made Newton simultaneously more conservative and more radical than the Enlightenment figure. Conservative, he believed truth was already known to ancients and must be recovered, not discovered anew. Radical, he rejected centuries of tradition, Trinity, Aristotelian philosophy, and accepted chronology as corruption of original truth. The real Newton, physicist, theologian, chronologist, decoder of ancient wisdom, pursued a comprehensive understanding that modern disciplinary boundaries cannot capture. His greatness lay not just in specific discoveries, but in the scope of his vision, the intensity of his pursuit, and his willingness to challenge every authority except evidence and reason. Newton's influence on philosophy: Locke, Hume, Kant, and beyond. The camera opens on a quiet study lit by candlelight. Shelves of leather-bound volumes rise in the shadows. At a simple wooden desk sits Isaac Newton, surrounded not only by geometric diagrams and prisms, but also by Hebrew Bibles, alchemical treatises, and manuscripts on the prophecies of Daniel and Revelation. This is not the narrow figure of popular myth, the lone mathematician under an apple tree, but a man who believed the whole universe, from the fall of an apple to the fate of empires, was held together by one intelligible design. From this room, Newton changed not only physics and mathematics, but philosophy itself. After him, thinkers had to ask a new kind of question. Not merely what is true, but how is the kind of knowledge Newton achieved even possible? In the late 17th century, European thought stood at a crossroads. On one side, the rationalists, figures like Descartes and Leibniz, sought to deduce the structure of the world from a few clear principles, as one proves theorems in geometry. On the other side, an emerging experimental tradition, shaped by Francis Bacon, Hooke, and Boyle, emphasized careful observation, experiment, and cautious generalization. Newton fused these strands. In the Principia, he showed how motion on Earth and motion in the heavens could be described by the same simple mathematical laws. In the Optics, he combined minute, painstaking experiments with prisms and lenses with bold theoretical inferences about the nature of light. To Newton's contemporaries, this was more than a scientific tour de force. It was a toward general laws.
Newton's refusal to indulge in unfounded hypotheses, summed up in his famous "I frame no hypotheses," resonated with Locke's caution in metaphysics. Both men were deeply suspicious of elaborate doctrinal or philosophical systems not anchored in what could, in some way, be checked against experience. Yet Newton's impact on Locke was not merely methodological. Newton's work suggested that nature operates through universal, stable patterns described by laws. Locke's own reflections on causation, powers, and the laws of nature unfolded in a world where Newton had shown that such laws were not only conceivable but astonishingly fruitful. Locke's distinction between those qualities of objects that seem to belong to them independently, like size, shape, and motion, and those that exist only in relation to our senses, like color and taste, found a powerful ally in Newton's optics. When Newton demonstrated that white light contains rays of different refrangibility, producing colors through interaction with matter and the eye, he reinforced the idea that colors are not simple properties painted onto objects, but complex effects emerging from more basic physical relations. A few decades later, another thinker, far to the north in Edinburgh, decided to take Newton's method and apply it to the human mind itself. David Hume admired Newton so deeply that in the introduction to his Treatise of Human Nature, he described his own project as an attempt to introduce the experimental method of reasoning into moral subjects. Hume wanted to observe the operations of the mind as carefully as Newton had observed bodies in motion, to identify the simple elements of experience, impressions and ideas, and the basic laws by which they associate. For Hume, the mind becomes a kind of laboratory. Just as Newton had shown that planets and falling bodies alike follow the same gravitational law, Hume sought to show that our beliefs and emotions, our habits and moral judgments follow general patterns of association. But as he pursued this Newtonian ambition, he stumbled upon a disturbing conclusion about one of Newton's central notions, causation. Newton's laws seem to capture necessary connections in nature. Force equals mass times acceleration, gravitational attraction varies with the inverse square of the distance. The world appears to behave as if bound by necessity. Hume, however, noted that in experience, we never actually perceive this necessity. What we see, strictly speaking, is one event followed regularly by another. The impact of one billiard ball followed by the motion of another, the striking of a match followed by the flame. The must that we feel, the sense that the second event has to follow from the first, does not come from the events themselves, but from the mind's habit of expecting B whenever A has been repeatedly followed by B. Under Hume's gaze, Newton's majestic laws begin to look more like exquisitely precise descriptions of constant conjunctions than windows into an inner necessary glue binding cause and effect. And the method by which those laws were discovered, induction from observed cases to general statements about how all bodies behave, faces an unsettling question. Why assume that the future will resemble the past, that nature is uniform? This principle cannot itself be justified by further induction without circularity. Hume thus exposes a kind of logical vulnerability at the core of Newtonian science. Its success is undeniable, but the rational foundation of its universal claims appears less secure than one might hope. In Königsberg in the late 18th century, Immanuel Kant read Hume and was, by his own account, awakened from his dogmatic slumber. But he also lived in a world where Newtonian physics had become the gold standard of certain knowledge. Kant's problem was to reconcile these. How could he acknowledge Hume's critique that we do not simply read necessity off the world, and yet preserve the apparent necessity and universality of Newton's laws? Kant's solution was daring. He argued that certain features of our experience, like space and time, are not properties of things in themselves, but forms of our sensibility, ways in which our minds must structure any incoming data. In a similar way, fundamental concepts like causality, substance, and quantity are not distilled from experience. They are a priori categories of understanding, rules according to which we synthesize the manifold of intuition into coherent objects and events. In this framework, the regularity and necessity we find in Newtonian physics are not illusions, but neither are they glimpses of things as they are in themselves. Rather, they are reflections of the conditions under which any empirical experience is possible for creatures like us. Newton's laws, especially as Kant understands them in his metaphysical foundations of natural science, become the highest-level articulations of how objects in space and time must behave if they are to be objects of experience at all. Contradictions and limits of Newtonian science. The camera now pulls back. We see Newton's work not only transforming philosophy, but also revealing its own tensions and limits. In Newton's day, many natural philosophers were committed to the mechanical philosophy, which held that all change in nature must result from matter in motion, bodies colliding or exerting pressure on each other. Distant effects without contact, action at a distance, were treated with deep suspicion as a return to the occult qualities of scholastic space with no mechanical medium specified. In private correspondence, he admitted that the notion of one body acting on another at a distance through a vacuum without mediation was so great an absurdity that he could not accept it without the intervention of something immaterial, which is not material. But in the Principia, he offered no such mechanism. He focused instead on the mathematical form of the law, its predictive power, and its grounding in observable phenomena. "I frame no hypotheses," he wrote, meaning where no mechanism can be deduced from experience, he refuses to conjecture. This choice marked a turning point. For some, it meant the end of the old mechanical ideal of explanation. Science while avoiding occasionalism, the view that God is the only true cause of everything, with natural causes being mere occasions for divine action. Newton believed there were genuine natural causes. Bodies really do exert gravitational force on each other. But these natural causes existed and operated only through God's continuous sustaining power. If God ceased to will the universe's existence for an instant, all would collapse into nothing. This theology had several important implications. 1. Action at a distance becomes comprehensible. If gravity is direct divine action, mediated through God's omnipresence in space, then action at a distance isn't mysterious. God is present at both locations, immediately aware of both bodies, and can coordinate their interaction without requiring material transmission. 2. Natural laws reflect divine rationality. The mathematical elegance of physical laws are mathematically precise true religion. His prophetic interpretation mechanics from planetary observations decoded historical prophecy from biblical symbols. The Prisca Theologia. Newton also pursued what scholars call knew God as absolutely one, rejecting the polytheism that later corrupted surrounding cultures. 2. Ancient heliocentrism. Pythagoras and other ancient philosophers knew the heliocentric system, that Earth and planets orbit the Sun. This knowledge was later lost or suppressed, requiring rediscovery by Copernicus. 3. Ancient science. Early civilizations possessed advanced astronomical and mathematical knowledge, evidenced in ancient monuments and texts.
studied through observation and mathematics, revealed God's rationality and power through natural law.
Served to make Newton safe, safely secular for the rationalists, safely Christian for the believers. The real Newton was neither, a passionate monotheist who believed physics revealed theological truth, a meticulous biblical scholar who rejected core Christian doctrine, a scientist mystic who sought ancient wisdom while pioneering modern methodology. The theological foundation of Newtonian science. Understanding Newton's theology is essential for understanding his science because the theology provided. 1. Metaphysical foundation. He was recovering spiritual, symbolic